Hello everyone, and welcome back to another GeoStats lecture tutorial video. And in this video, we're going to cover the idea of nearest neighbor interpolation. And if you remember back to our conceptual video, we said that the easiest way to implement this is through the idea of Verneuil polygons, which would basically let you visualize all of the areas that are closer to one point than any other. And that's nearest neighbor interpolation. So what we're going to do is we're going to use the library Dismo for its Verneuil polygon method. GStat is going to provide us the data, and then SP and SF are just the required spatial structured data libraries. So we'll call in all these libraries. We're going to need to call in first our data. So our data, like I said before, is going to come from GStat, and it's going to be the Fulmer data set. If we run that, we have 1,324 objects of 6 variables. So if we just run a quick head on Fulmer, you'll see here that we have X and Y, so these are the coordinates. And then the variable that we're going to be interested in here is this Fulmer variable here. So this is what we're going to be doing all of our interpolation based on. So the first thing we need to do is take this data frame and convert it into something spatial. So we're going to do that by doing SPDF, by using the SP packages spatial points data frame. So this is going to create a point data set with a data frame. And just quickly, you can see that it requires chords, and the chords is going to be a cbind of Fulmer $X for the X coordinate and Fulmer $Y for the Y coordinate. So again, I'm just pulling out X and Y here, creating a new data set here to pass into chords. Then we need the data, which is the actual data frame that is going to go into the points data frame. And this is just going to be Fulmer. Okay. And then finally, because this is a spatial data set, it needs a project for string or proj for string. And this is actually going to be requiring a CRS object, which this is coming from the SP package as well, not PS, SP package as well. This converts a project argument like this. So this is just a standard definition of the projection that I know goes with this data. I would not expect you to have known this in advance. I just happened to look this up and figure it out. So anyway, if we run this, you should see that we get a formal class spatial points data frame. So we've now taken this data frame here and made it spatial. So the next thing that we need to do to create a nearest neighbor is to take this spatial points data frame and actually run the Verneuil polygon. So I'm going to call this VP for Verneuil polygon. And then we're going to call Dismo, which is the name of a package that has the Voronoi function. So you can see that Verneuil takes in an argument xy, and that is the spatial object. In this case, we're going to pass in SPDF. And if we run that, it's loading a required package that we didn't specify called deldir. And we will see that it ran without any errors. Again, that was a warning. It didn't fundamentally impact our ability to run the function. So now that we have that, and we can just quickly plot just to make sure that we actually have what we think we do. Those are Verneuil polygons. You can see they're kind of messy, but that's okay. Now what we need to do is we need to actually attach the data, right? Because right now they're just shapes. So in order to do that, the easiest way is going to be to use the join function in the SF package. So what we have to do is we have to convert to SF. So we're going to do f_SF, and we're going to use the SF function st as SF. So this will basically convert any other sort of data set to an SF version. So we're going to convert the SPDF function. So this is going to allow us to convert that. That's perfectly fine. We don't need to worry about that error message for now. Next, we need to convert the polygons because they are also currently right now a SP version, so they have to be SF. And then if we call SF : ST underscore as SF, and we're going to do the same thing. We're going to pass in as our X the VP per Voronoi polygon. Run that. Okay, so we now have two SF datasets. Now we're going to run the join. So we're going to call this VP underscore join, and we're going to call SF underscore ST underscore join. This is a spatial join. It takes in two parameters. The first is X, which is the first geometry. This is the geometry that you want to join to. So this is going to be the geometry of the output. And then Y, which is the second geometry that you want to use to join. So we want to make sure that our X is the output geometry. So in this case, we want everything to be joined into the Voronoi polygon. And we want our Y to be joined by the Fulmer dataset, which we call FSF. So just to recap here, this is a spatial join between the polygons and the original point data. So if we run that, you'll see that we now have a VP join. And if we go ahead and we call a tmap of I don't think we actually loaded the tmap. Let's just really quickly load the tmap library. Okay. We now have tmap joined. So we'll call tm underscore shape. And this is going to take in a shape, which we're going to pass in as the VP underscore join. And then I want to call in the tm underscore polygons. And I want to derive color from the variable we're going to call the variable in from, make sure we get our naming right here. So we want to do VP join. We want to call in Fulmer.x. Oh. Okay, and then if we call tmap, plot that, you'll see that we see our, we've pulled in the data set and we now have our nearest neighbor interpolation. Hopefully that makes sense. If any of this doesn't, I encourage you to pause the video, go back, rewatch the parts you're confused about, and as always, please reach out. Thank you.